Okay, welcome back. Happy Friday. Today we're going to change things up quite a bit. The last class we talked about solving quadratic equations using factoring. The two classes before that, not counting the quest, were all about factoring. Today, something completely different. We're going to be graphing. So we're going to be plotting some points and learning all about the key features of a new kind of graph called a parabola. I think this is the first graph we've seen this semester that wasn't just a straight line. So today we'll be graphing curvy things. And then just a sneak peek, the next 2 days coming up are about the quadratic formula. And then we can see the word quadratic again pop up the class after that. And then it's a little ways away, but quest number 4 is happening on April 23rd. Questions on the calendar? Okay, then let's jump up here towards the top of page 44, and we'll begin with number 1. Can we go to Brandon? Yeah, we call the graph a parabola. Let's go to Alex. Okay, so let's see if we can quickly fill in a bunch of this table, and then you guys are going to plot a lot of points. So the first equation is right up here. Y1, I'm calling it Y1 just to separate it from the other two equations, is equal to x squared. So for example, if you plug -3 in for x, -3 squared is 9, right? Because you're squaring the negative. And then -2 squared is 4, and then -1 squared is 1. 0 squared, 0. 1 squared is 1, 2 squared is 4, and then 3 squared is 9. And so each of these gives rise to a point. So the first point is -3 for the x, 9 for the y, right? So just fill in the rest of that column with all the points that we just found. And we're going to plot them in a second, but let's fill in the rest of the table first. Okay, next equation we're going to do is this one right here. Y equals -x squared. So that means you're going to take the x, you're going to square it, and then you're going to make it negative at the very end. So if I plug -3 in, what do you get when you do -3 squared? It's +9. So I'll write this one out. So it's -3 squared with an extra negative sign sitting in the front. So it becomes +9 when you square it, but that negative sign in the front changes it to -9 at the end. And then we'll do -2 squared. That becomes +4, but then a negative sign at the end makes it -4. How about the next one? It's -1. In fact, do we see the relationship between this column that we're building and this column that we already had? What's the relationship? It's just the negatives of whatever we got, right? Makes sense. These were x squareds. These are negative x squareds. So we're just going to copy those numbers and make them negative over here. So 0 there, -1, -4, and -9. And again, each of these guys gives rise to a point. What are the coordinates of the first point? How much is x? -3. How much was y? -9. Go ahead and fill in the rest of that column, x comma y. Okay, and then let's move on to the last one, which is this y3 equals 2x squared. Do this one in green. Okay, so let's try the first one. So it's supposed to be 2 times x squared, and the first x is -3. So it's this. Is the first thing we do that multiplication or the square? Square. We know exponents come before multiplication. So this is really 2 times. So this one's 18. And 2 times 9 is actually just 2 times the guy from the first column, right? And in fact, that's kind of the shortcut way to do this one too, is that all we're doing is doubling the x squareds that we got in the first column. So we're just going to double those numbers in the far left. So what's the next one? Doubling the 4 is 8. Doubling the 1 is 2. Doubling 0, 0. And then 2, 8, and 18. And again, each of these gives rise to a point. So the first point, x was -3, and y was 18. So fill in the rest of that column with all the points we just found. And when you're ready, you're going to start plotting points. So what I'd like everybody to do first is just plot these first points that I have up here in red. Right? So the third column in your table. So just plot those 7 points on the axes, and then we're going to connect the dots with a smooth curve. So we plot our 7 points, and then we connect them with some smooth curve. Looks like this curve goes down for a while, and then bottoms out at the origin, and then comes up, and probably continues on up on both sides, okay? And like we read in the very first line at the top, the graph of this thing is called a parabola. So you are looking at a parabola. Okay, so that's your basic y equals x squared. I'm going to write that equation here. And now we're going to graph the points that are in blue, which is like the middle set of points that you have. So let's see if we can plot these ones in blue. So the first one is -3, -9, and then you're going to plot the rest of them. So I don't have my 7 points plotted, but I'll just ballpark it. What's the relationship between the y equals -x squared and the original one? Flipped over what? Over the x-axis, right? That's sure what it looks like. So the graph that you draw should be symmetric, flipped over the x-axis. So yeah, x-axis. Okay, and then the last set of points, I started them up here in green. They should be the rightmost column for you. So the first one is -318, which is actually going to be off the grid, so you have to just estimate where that is. But go ahead and plot your 7 points from the last column, and then we'll connect the dots there too. So I've plotted my 7 points up here in green, and I've written the equation in green, y equals 2x squared. Can anybody describe the relationship between the green and the original red? Or what? Skinny. Looks skinnier, right? Right. The red one just got skinnier, narrower. That's a perfectly fine way to see that. Does anybody see the green compared to the red as something different than skinnier? Narrower, yeah. Steeper is good. Any other thoughts? Which two? The red and blue? No, I think that the green has a nice relationship to the red. I'm going to throw another word out there, and skinnier is perfectly fine. Victor? They do open in the same direction, and we'll talk about how they both open up. I'm going to use the word taller. Use the word taller, and I'm going to try to convince you that it's also valid. Take a look at this point right here. Do you see how there's a corresponding point that went up higher than it did? And this point right here, I could think of as going up. When you guys say skinnier, you're saying, oh, these points all went inwards, right? Horizontally. But you could also look at this as being a vertical. It turns out they're both correct. Both interpretations here are correct. You can say that it's gotten skinnier. You could also say that it's gotten taller. Oh, what happened to all my stuff? Okay. All right. So these are some very basic parabolas. On the next page, we're going to look at some not as basic parabolas. And we're going to talk about some of the distinguishing features of these curves. So down here, I've got 3 different graphs. Now, it's going to be easier to look at the board and look at the colors, but I tried to give you a solid one and a dashed one and a dotted one. So even in the black and white copy, you could still tell them apart. So here are the equations in some order. Y equals 4x squared minus 4, y equals x squared minus 14x plus 60, and y equals negative x squared plus 10x minus 25. So the equations are a lot more complicated than they were before. So the first thing I want us to do is figure out which one is which. So what if we do this? What if we just let x equal 0 in each of the equations? How much do you get when you plug 0 in for the first equation? Negative 4? Which means that there's a point we've just found that's on that graph. How much was the x that we started with? 0, and the y turned out to be negative 4. So if you can find the graph that goes through the point 0, negative 4, then you have found y1. So which color is it up on the board? It's blue, right? Because the point 0, negative 4 is presumably that guy right there. Okay, so I'm just going to write y1 is this one. And let's do the same thing with y2. Again, plugging 0 in. You could plug any number in, but 0 is just so easy to plug in that we'll do that one. When you plug 0 in for y2, what do you get? 0 in for the x's, I should say. 0 for x, 0 for x. What's the whole thing turn out to be? You're doing the last one. I want to do the middle one first. 60, right? Because a 0 squared disappears. 14 times 0 disappears. So we just get 60, which means 0.060 is on one of these graphs. It's green. So this one right here is y2. Okay, so I guess by process of elimination, we know which one is y3, but when you plug 0 for the x's in y3, what do you get? I get the negative 25. So this one definitely hits the point 0, negative 25. Does that confirm our choice for red? 0, negative 25, that seems reasonable. So that one right there is y3. Yes. Thank you, Karen. 060. Okay, so 3 complicated equations, and they're 3 graphs. We figured out which one is which. And now we're just going to talk about some of the relationships between the equations and the graphs. And the ultimate goal is to be able to take an equation and from scratch generate that graph. That's the goal for today. So first observation, what are these points called? 0, negative 25, 0, 60, and 0, negative 4? What are they? They are coordinates, it's true, but they're special coordinates because it was that point and this point. What are those points all called? Those are all y-intercepts, right? We know that the y-intercept is where the graph hits the y-axis. So it feels like there's a nice little shortcut here to find the y-intercept if you know the equation. could we have found, let's look at just this middle y2 equation. Could we have gotten the answer, which was 60, without actually plugging the 0 in? Do you see the 60 sitting in that equation? Where is it? It's the last thing right at the very end, right? Is that true for the y3? Is the negative 25, and then for the y1, it's negative 4. Okay, so that's kind of neat, is that the last number right there is always the y-intercept. I'm going to write it. It's not something you need to memorize. I mean, it's like a, I guess it's a tiny shortcut, but you don't need to memorize it. But we're just kind of discovering things here. So if you have y equals ax squared plus bx plus c, which is our way of writing the most general kind of equation of that form as possible. A, b, and c are just numbers. Then the y-intercept is, okay, it's got two coordinates. How much is the x for any y-intercept? 0. And then the answer to the y-coordinate is one of those letters. It's c. That's it right there. The y-intercept is always 0, c. Again, it's not something to memorize, but we're just exploring these new things. Okay, next observation has to do with something that Victor shared with us. Victor talked about parabolas opening the same way. So take a look at blue. Would you say that blue opens up or down? Not a trick question. Blue opens up. What about green? Green opens up. What about red? Opens down. There must be some inherent difference in the equations. Something that the blue and green equations have in common, but that the red equation has something different. So let's just look. I'm going to come up here and I'm going to circle these equations. Let's see. So we said the first one was the blue, so I'm going to circle that in blue, and then yeah, that's fine. And then green was y2, and then blue, no, red was y3. Okay, can anybody look at those three equations? Blue and green are supposed to have something in common that apparently makes them open up, where red has something different that makes it open down. Alan says that red has a negative in front of the x squared. And blue and green both have positive numbers in front of the x squared, right? It's a 4x squared and it's a 1x squared. And that's exactly the thing that tells you whether you open up or down. Everybody see it? So let's see if we can write it. Okay, A, B, or C, which is the thing that we've just decided governs whether it opens up or down? It's the A. If A is a certain kind of number, then it opens up. What kind of a number? Positive. If A is positive, then the parabola opens up. And then there's a very similar sentence. If A is negative, then opens down. Okay, so far so good. Again, not a whole lot that I'm going to ask you to memorize in this list, but we're just figuring things out for these new creatures that we haven't thought about before. Okay, next thing I want to look at is the blue, and in particular, I want to look at the x-intercepts. Can you guys put a dot on each of the x-intercepts for blue, which was the solid curve on your page? And once you've got your two dots, right next to the dots, write the coordinates of those two x-intercepts. me, it looks like they're -1, 0 and +1, 0. Okay. What's true about any x-intercept? The y is equal to 0. This is something we knew from before. To find x-intercepts, you would let y equal 0. Okay, it's still going to be true. And in fact, I think it's written down here. Where are we? This is in part C of something we're about to look at. But to find the x-intercepts, you set y equal to 0. Of course, that's what we've done all semester to find x-intercepts. Okay. The only other characteristic that I want us to focus on for today is that each of these three graphs has a turning point, a point where the behavior changes. So if you are, say, out for a run and your neighborhood street looks like this, and so you're quite enjoying life as you run on this very easy, steep downhill, and then it starts to flatten out, and then what happens? And then you pay for it because the road goes really, really steep uphill. And so I would say there's something special going on right down there at that bottom point. At that bottom point, as a runner, you're not really happy or sad. It's flat for just a moment, right? Just come off the downhill, about to tackle this massive uphill. But that point down there at the bottom is the place where things change, downhill to uphill. Same kind of thing for green. Can you guys put a dot on the turning point? Put a dot on the point on the green, which is the dotted parabola, where the behavior changes. Goes from decreasing to increasing, downhill to uphill. And once you've got that point, just estimate the coordinates. They're not going to be perfect, but just estimate. It's this one here. Okay, any estimates? What'd you guys get? 7 and 10? Seems fair. Anybody else have a slightly different estimate? 711, 712, 7 what? 715. Okay, so we're all in the ballpark. It's hard to know. We don't have a fine enough scale to know exactly, but that's the turning point. Now the same thing for red. Red would feel different for the runner. For this runner going left to right on that red street, what would the beginning of the run feel like? It would be hard because we're going uphill. And then we get to that top, the peak of the mountain, and then we're really happy because we've got this downhill coming up in front of us. So go ahead and put a dot on the turning point for red. And then estimate the coordinates of that point. What do we think? Looks like 5, 0 to me. The two of those three turning points behave the same. For blue and green, it goes downhill, then to the turning point, then uphill. The red one is different. It goes uphill, then the turning point, and downhill. But the important thing is it's a turning point. It's either the highest or lowest, and it just depends on whether you're opening up or down. Okay, last observation, and then we'll start really graphing these things. Suppose that, let's come over here. I'm just going to plot a couple of points, just making up some points here. Suppose that I put a point here at 10 and another point over here at 14. And I say I'm thinking about a parabola and it hits those 2 points. Now I'm not telling you whether this thing opens up or down, and I'm hoping you guys can envision that both are possibilities. Could you draw a parabola that hits those 2 points that opens up? Could you draw a different one that opens down? Yeah. Could you draw more than one that opens up, or is there just one? More than one. How many are there? There's infinitely many. Yeah, I mean, you could have the parabola, again, you don't need to draw this, but this parabola could be really, really wide, really shallow, and just kind of not do too much different between those intercepts. That's one possibility. But another possibility is that this thing is like coming, screaming downhill, and then it bottoms out someplace, in the basement of this building, and then it comes screaming back up and hits there, right? And everything in between. There are infinitely many different ones. But here's something that we can say is true about all of them. If the x-intercepts are at 10 and 14, can you tell me what the x-coordinate of the turning point is. In the first one, the turning point looks like it's around here. In the second one, it's, someplace in the basement down there. What's the x-coordinate of the turning point? It's 12. It's 12. How do you find the turning point if you know the two intercepts? You go right in between, right smack dab in the middle. So if we happen to know the two x-intercepts are 10 and 14, we can just go right in the middle and say the turning point is at 12 something. It could be 12 negative 1, could be 12 negative 1,000. I don't know, it could be 12 500. I don't know, but it's definitely 12 something. So was that true over here? I've got my two x-intercepts in purple. What do you get if you average the x's? You go right in the middle of these two x numbers. We get 0. If I look at that red turning point down there, would you guys agree that it's definitely at 0 something? Halfway in between those two x-intercepts. Okay, so we said lots of stuff. Let's see if we can finally give one more vocabulary word, and then we'll sketch. Number 3, we'll go up to Alexa. Okay, so we did that already. The new thing there is the word, vertex. So I've been calling it a turning point, but really it's called a vertex. Okay, so here is a 6-step process that we're going to follow in order to sketch. We're not going to read all the details now, but we'll come back to them as we actually do an example. Part A talks about whether the parabola opens upward or downward. We discussed that already. Part B says find the y-intercept. How do you do it? You set x equal to 0. That's always how you find the y-intercept. Part C talks about finding x-intercepts. How do we do that? To find the x-intercepts, what are we doing? Well, that y equals 0. That's what we've done all semester. Part D says find the x-coordinate of the vertex. How are we going to find it? Well, we've already got the x-intercepts, and we just said that that turning point is halfway in between. So all you got to do is average. That's the halfway in between. Average the x-intercepts. Turns out there's an easier way to do this, and we'll see it soon, but for right now, the only tool we have is averaging the x-intercepts. Part E talks about finding a symmetric point. We'll do that with an example. And then part F, you plot all the points that you just came up with, and then you connect them in some smooth curve. So let's give it a shot. Number 5, we've got 2 examples here. First one is y equals x squared minus 4x plus 3. X squared minus 4x plus 3. Okay, so let's see if we can do this step-by-step process. You guys are going to have to remind me of the order. But the first step, up or down. So remember, to decide whether it opens up or down, you're looking at the number in front of the x squared. What kind of a number is that? Positive, which means it opens up. Okay, so I'm just going to write this. A is equal to 1. Remember, we were calling A the thing touching the x squared. And 1 is a positive number. Here's the shorthand way to say it's a positive number. It's greater than 0. So the parabola opens up. Okay, part B has us finding the x-intercepts. To find the x-intercepts, you do something. What do you do? Sorry, that is not part B. Part B is the y-intercept, right? We'll find the y-intercept first. It's always easier to find the y-intercept. That's why I have it first. So what do we do whenever we want to find y-intercepts? If you let what equal 0? X, the other letter. So we'll let x equal 0. Let's give that a shot. So we're just rewriting this equation, but all of those x's become 0. So it's 0 squared minus 4 times 0 plus 3. How much is that? 3. So the coordinates of the y-intercept are 0 and 3. And we actually did discover a neat little shortcut that we didn't use but could have. Could you look at the original equation and just know that it's going to be 0, 3? Remember we had said it was the last number sitting by itself is always the y-intercept. So you're welcome to use it. I don't need you to memorize it. It takes like 10 seconds to figure it out. Okay, that's good. Part C is finding the x-intercepts. Finding x-intercepts always starts the same way. Let y equals 0. So we're going to go back to that original equation, and we're going to change the y to 0. So I copy everything on the right, and I just change a 0 on the left. 0 equals x squared minus 4x plus 3. Everybody see where that equation comes from? Okay. Finding x-intercepts is harder than finding the y-intercept, because here we have some algebra to do. We've got this quadratic equation. It's got an x squared, so it's quadratic. How do we solve this equation? What's that? We split it into 2. Can somebody give me a different word for what Yurka is describing? Is factor. That's what we have to do, right? It's an x squared equation. So factoring is the right idea after you got a 0 on one side. It happens to already be there. So we have to factor this thing. And I'm hoping that even though it's been like 3 class days since we introduced this factoring idea, that it doesn't just disappear and fade. Like we're going to keep using this factoring idea. So hopefully this is getting easier, more natural for us. Is this the easier product sum case or the harder box? Easier because of that 1. Product is 3, sum is -4. X is in both, and then we just got to find the magic numbers. Multiply to 3 and add up to -4. -3 and -1 is correct. Now, for some of you, I'm sure that is still mysterious. So if that's mysterious, put a star next to it and verify it later on. You got to be able to factor. Okay, but now it looks like the problems we did last class. We've got a factored version equal to 0. So what do we do to go on to the next step? Set each individual piece equal to 0. Guys remember that from last class? So it means either 0 is x minus 3 or 0 is x minus 1. Each piece equal to 0. And then we'll solve for x. Add 3 to both sides. X equals 3 is one answer. Add 1 to both sides on the other one. And x equals 1 is the other answer. Okay, and because we're going to plot these, let's just go ahead and write them as ordered pairs. For the first point, how much is x? It's 3. How much is y? It's really tempting to throw that 1 in there. It's 0, because the very first thing we did was let y equal 0, right? So it's really easy to just write the point 3, 1, like it's one single point. It's not. There's two x-intercepts. The x-coordinate on the other one is 1, and the y is also 0. Okay, those are our two x-intercepts. Again, x-intercepts are definitely harder to find than y-intercepts. So expect to pause at that step. Okay, I think part D, can somebody go back to the previous page? Was it about finding the vertex? Yeah. Okay, so we've got these two x-intercepts. In fact, why don't we just pause here and plot some points? So the first thing we had was 0, 3. So plot that point, and then plot these points down here, 3, 0, and 1, 0. Just based on those 3 points, if you could try to imagine the rest of the parabola, is it opening up or down? Up, right? Can you see that the only way to connect these with a parabola is to open up? So that confirms what we did first in part A. And that means that the vertex is someplace down below the x-axis, right? Kind of envision it just dipping down below the x-axis a little bit. So how would we figure out where that vertex is? Could the vertex be over here? Could this be the lowest point on the parabola? No, it's definitely between what two numbers? The 1 and the 3. And in fact, I don't know how low it is, but I know exactly what the x is. How much is the x at that vertex? Is 2. It's not just between 1 and 3, it is perfectly between 1 and 3, halfway between 1 and 3, which makes sense. I mean, like if you just try to draw this guy, like it's going to bottom out right there at 2. Now, I'm just estimating, so don't connect yet. We don't have enough info, but it's definitely 2 comma something. So I wanted to write the details of that. Part D is to find the vertex by averaging the x-intercepts. Ooh. Is the line going to be symmetrical? Which line? Yes, parabolas are always symmetric, whether they're up or down. Okay, so we're averaging 3 and 1. Now I know the answer is 2 because it's easy in this case, but if it were harder numbers like 3.6 and 1.75, what's the process you would go through to average two numbers? Add and divide by 2. So we'll do 3 plus 1 and then divide by 2. Right, that's how we find the number in the middle. So 4 divided by 2 gives us the 2 that we knew was going to be the answer without doing that calculation. But the calculation will always work in case you don't know what the average is. And I guess I'll put an x equals in the front because that 2 isn't everything about the vertex. It's just the x of the vertex. Okay, how do I find the y of the vertex? I know that x is 2. And I also know the equation. It's right here at the top. So how would you find the y when x was 2? Plug it in. We just substitute x equals 2 into that equation. So let's do that here in part D. Okay, so the equation was x squared minus 4x plus 3. Is that right? Yes? Yes. Okay, so what are we plugging in for those x's? So we just have to do calculation, and then that will get us the y value. So here we have 4 minus 8 plus 3 works out to -1. So that means the vertex is, and again, it's got 2 coordinates. What was the x? 2, we found that first, and then what was the y? -1 is what we just got. And then plot the point to -1, and it should line up, like it should be reasonable. If your vertex is like way far away from the rest of the points, there's probably a problem. But to -1 seems reasonable, right there. And so now we can really see the parabola taking shape. Let's find one more point. Who had mentioned the symmetry? She asked if parabolas always have symmetry, and the answer is yes, they do. And so I'm going to draw the line of symmetry here. The line of symmetry here, is it a vertical line, sorry, a horizontal line that we flip over, or a vertical line that we can flip over? It's a vertical line. So I'm going to draw the vertical line. And of course, the vertical line goes right through that vertex, right through the turning point. And so the last point that we should plot is the one that seems to be missing. It's the counterpart to which point that's already here. The y-intercept, right? Like the x-intercepts, they already match up. The vertex is the only one at the dance without a partner, right? Everybody else has a partner, but the vertex doesn't have any. And so the y-intercept seems to have one that's missing. So can you look at this and figure out what the coordinates are of the missing, the symmetric point? It's 4 and 3, right? So I'm not going to talk about like how we got that. I mean, I'm hoping that you can just look at it and figure out. You're just trying to flip that point through 0, 3 over the line. And so we get this other point over here. Looks good at 4, 3. That feels right to me. And once you've got 5 points, connect the dots with your smooth curve, and you've got your parabola. Make sure when you're plotting, when you're graphing your parabola, that you don't do this. What mistake have I made? I stopped it. I mean, this parabola goes forever, right? I mean, it would be, I don't know if arrogant is the right word, but like for the parabola to exist only where I picked points, that seems a little bit arrogant to me, right? This parabola goes forever. We just picked a few representative points. So please make sure that your parabola extends past the edges of the graph paper. If you don't put arrows at the top, I won't take points off. But if you stop it at points that you plotted, I'm going to take something off. Any questions on that? Okay, so it's a multi-step problem. They take a while. There was one more example I'm going to do. I don't think we need to. I'm just going to say for the group activity, which you're about to do, you have this 6-step process that we've just gone through once. You're going to give it a shot starting on the next page. So the group activity is there on 47 and continues on 48, and there is an answer key. Raise a flag if you get stuck, check in with each other as well, and I'll check homework.